today, so I'm about to solve the hemisphere problem. Okay, so I will just write a short title for it. So radiation from a sphere with plus minus v cosine omega t potential. Okay, so that's the title I gave it. So this is Jackson, I guess 9.3. And if I draw the problem, it looks something like this. Okay, so that's the problem that we're dealing with. And let me actually do a little bit of background before I jump into solving it. So basically what we're going to start with is, well, you can write a vector potential. So if you really start from the beginning, but I'm going to just jump over some steps, you have a vector potential, which is of the form d3r prime dt prime, and here you would have j r prime t prime divided by r minus r prime. And here you would have a delta function, which connects the two time points, the time point at which the radiation is radiated from the source and the time at which it's detected by whatever probe that you are using. So it's t prime minus r prime divided by c. So that's what you would start with. And then you would write j r prime t prime as j r prime e to the minus I omega t prime. Okay, so what this is well, we're just giving it a harmonic form for the time dependence. And then we can actually do this integral. And what we get is well, actually, ART will have the form e to the minus I omega t over, sorry, there's a 1 over c here, which I forgot. So 1 over c. And here you would have d3r prime j r prime e to the I k r minus r prime divided by r minus r prime. Okay, so what I did is I integrated over this delta function, and I used the fact that k wave vector is omega over c. Okay, and then my next step is actually to assume that basically the source is small compared to where we are at, okay? But I'm not making any other assumptions. But nevertheless, what that does, at least up to first order, is, first of all, there's actually one other thing I'm going to do. I'm going to forget about this e to the minus I omega t, and I'm only going to keep the r dependence. So no t dependence. Let's forget about the t dependence. And basically, we have e to the I k r divided by rc integral j r prime dr prime. Okay, so that's almost the starting point where we're at. Okay, but not quite. There's actually one more thing that I want to do, which is to take this integral and convert it into a different form. So I can take j r prime d3r prime. I should have written it like this here too, and I can write it as minus j r prime, sorry, divergence of j r prime. Let me write that again. So I can write that as minus r prime divergence of j r prime d3r prime. Okay, and so that you can prove by integration by parts for all components involved. And then by the continuity equation, we can write that this is actually integral r prime, the partial rho r prime, partial t, d3r prime. And then we can also invoke a time, this is actually, sorry, this is actually time dependent, of course, but we will invoke a time dependence of the same form as we did for the current, okay? And then this actually becomes minus I omega integral r prime rho r prime d3 r prime, which indeed is just minus I omega times the dipole moment. Okay, so that's our that's going to be our starting point. So what I have here is that the vector potential has the form. Well, I can write again using the definition of k as minus I k e to the I k r divided by r and dipole moment. Okay, so that's actually our starting point for solving this problem. Okay, now how do I connect this with a dipole moment? Well, basically from the form of the potential, we do expect a sizable dipole contribution, but as it turns out, what we're also doing here is we're neglecting higher order terms, and that's justified by the fact that they have a larger 1 over r dependence, so 1 over r squared, 1 over r third, and so forth. So we can actually forget about the higher order terms, provided that we're far enough away, okay? So the first part of this problem is good to solve for the dipole moment from which we have the vector potential. And then, of course, let me actually just tell you briefly that from the vector potential, you can obtain the magnetic field and also the electric field. Okay, so and then we can do the rest of the problem. These we're going to obtain in the also in the far zone limit. Okay, okay. So let's calculate this dipole moment first of all. Okay, so what I have is a sphere. Now the point is that keep in mind one thing. So basically, I crossed out the time dependence here. So both sides of this are multiplied by e to the minus I omega t to get a time dependent vector potential. Okay. However, this equation stated thus is a time independent equation. Okay, we can, if we want, we can put in the time dependence later. All we need is a static dipole moment. All we need is a static dipole moment. So we're going to use a static potential to calculate the static dipole moment. Okay, so the strategy is as follows. We're going to partly solve at least this problem. And you know that for this problem, the static potential, and we did this actually in another a long time ago, but the static potential is of the form, let's say AL over RL plus 1 PL cosine theta. Okay, so that's the form of the potential. And what we're going to do is, since we're only interested in the dipole moment, we're going to approximate this potential as, so approximate it as A1 divided by R squared P1 cosine theta, or A1 divided by R squared cosine theta. Okay, so that's our approximation. Okay, and then we have to actually find the A1 that best reproduces this potential. Okay, and that, of course, you do by what is sometimes known as the Fourier trick, or using the orthogonality of the p functions, or the orthogonality condition of the p functions. What you can do here actually is to integrate both sides. So I'm going to say A1 r squared cosine squared theta sine theta d theta. So I integrated this side, and then I'm going to also integrate the other side, but you see that this is an alternating potential. Sorry, this is an equal sign. So I can actually integrate just one side twice. So let's say from 0 to pi over 2, sorry, rather. So 0 to pi over 2. This actually goes from 0 to pi. Okay, so 0 to pi over 2. And what do we need here? So we need 1 cosine theta, a v, and the sine theta d theta. Okay, so okay, so that actually um, starts. So let me actually say, be a little bit more general here. So what I was doing here is to use this relation. Okay, so basically, but I'm only doing it for L equals 1. So you know that the relation that PL cosine theta, P, sorry, PL prime cosine theta d theta sine theta, that's 2 over 2L plus 1 delta L prime. So this is the for a general potential with all the terms, this is the relation that you would use. Here I'm just doing it for A1, so it's enough to do it for P1 cosine theta, which is cosine theta. Okay, so that's that. Sorry, of course this is on the surface of the sphere where we have this potential of plus v and minus v. So this was wrong. This should be a capital R. Okay, so anyway, let's integrate it. So on both sides, I can do a variable transformation. So x is cosine theta, dx is minus sine theta, d theta. Okay, so on this side, I'm going to have, so I do it on the next page, a1 over r squared, and minus 1 to 1, x squared dx. And that's equal to 2 times v, 0 to 1, x dx. Okay, so that's that. And if I do this integral, so I will get a1 over r squared, 2/3. And here I will get x squared over 2. So here I'm going to have 2v over 2, I guess. Yeah, it seems so if I do this integral, it's x squared over 2 from 0 to 1. That's 1/2. So this is actually v. So we determine that our a1 is equal to 3vr squared over 2. Okay, so our potential here is of the form 3vr squared over 2, 3vr squared over 2 cosine theta over r squared, which I can also write as 3vr squared over 2 z over r cubed. Okay, so all of these are different forms of the potential, and you know that a dipole potential, a dipole potential is of the form P dot R divided by R cubed. So, and if the dipole points in the Z direction, then we can write PZZ over R cubed. So our dipole moment is going to be 3VR squared over 2 Z unit vector. Okay. Okay, so that's the dipole moment that we will need. And now let me go back to the vector potential. So here's our formula for the vector potential, from which now we are ready to extract the fields B and E. Okay, so that's going to be our next step. Okay, so in order to do that, so let me remind us of the basic stuff that we have. So we have a dipole moment, which is 3vr squared over 2z. And we are also given that the vector potential for this dipolar case is some function of r times p. And the function I can also, of course, remind us, because we already derived this, is going to be minus ik e to the I k r divided by r. Okay, so that's it. Okay, so actually, it's not too difficult to derive the b, and we're going to implement the large R limit while we're doing all of these calculations. Okay, so let me say B is curl of A. Okay, B is curl of A. And so basically, that's going to be, I would do it like this, so I would do it in rectangular coordinates, partial x, partial y, partial z. And here I have 0, 0, because this pz only has a z component. And I'm going to write, well, I will just write f of r times p, okay, where p is actually given by this magnitude. Okay, so that's, we can start like this. And what are we going to get? We're going to get, for b, that it's x, and it's partial y of this. So it's actually p partial f partial r, partial y, which is y over r, minus, so we're going, that's this term. This does not give a contribution, but for the y, this does give a contribution, which is partial f partial r x over r. Okay, so that's, so I'm going to write this in a simpler form. Sorry, I made a mistake. Actually, this x should not be out here. Let me do this again, just to, my first contribution is x, unit vector, partial y of this. P is a constant, but I have to take the derivative of f of r with respect to y, which is going to be a derivative of f with respect to r and the derivative of r with respect to y. So P partial f partial y, okay? And then I'm going to have another contribution, which is, so this does not give a contribution, but when I go y, then partial x partial frp does indeed give a contribution. So it's going to be y p partial f partial x. Okay, so what we're going to have here is p f prime, and then it's going to be x y over r minus y x over r, where x is a unit vector, x hat is a unit vector, y hat is a unit vector, y and x are components, okay? And the interesting thing is that we can actually convert this immediately into spherical coordinates. Okay, so because this is obviously a phi component. So what I can do is to say p f prime, and I'm going to multiply upstairs by sine theta, okay? And then I'm going to have here x y minus y x divided by the square root of x squared plus y squared, because this square root of x squared plus y squared, of course, is r sine theta, okay? And basically what I get is minus p f prime sine theta phi. Okay, so as we radiate out in the r direction, we have a a magnetic field which is actually in the phi direction. Okay, we have one other thing to do, but actually, you know what? First of all, before I go further, let me take this f prime, which is, so what was f prime? F prime, of course, was the partial derivative of f, and here we have f with respect to r, but I'm also going to keep the limit that we need. Okay, so actually what this is minus ik, and then ik e to the ik r divided by r, okay, and then minus e to the I k r over r squared. Okay, so basically, what can we do here? So this is going to be minus k squared e to the I k r over r, and we have this other term, but if r is large, actually, we can neglect the second term. Okay, so we can just keep this one. Okay, so for f prime, we will just keep this term and keep going. Okay. Okay. So now we go on to the second part, which is the electric field. So we're going to now determine the electric field, okay? And in order to determine the electric field, I'm actually going to use the curl in in spherical coordinates. Okay, because what I have here, so let's remind ourselves, we found that this is minus k squared p, and this minus k squared p e to the I k r over r sine theta. Okay, let me actually simplify this. So that's the phi component. And I suppose I could simplify this by saying this is minus some function g of r times, so everything else is just swallowed in there, and sine theta. So that's the form that I would take. And we know that E is actually I over K curl of B. Okay, and here I'm going to need the curl in spherical coordinates. Okay, so this is r sine theta phi over r, and then partial r, partial theta, partial phi. Well, now I don't have to write anything here because this only has a phi component. So I have 0, 0, but here I have to multiply by r sine theta. Okay, so this is going to be minus gr sine squared theta. Okay, so because this here is r sine theta d phi. Okay, so that's actually that's the next step. That's the next step to deal with. Okay, so and I specify g. Okay, so because I just define g here, g is actually k squared p e to the I k r divided by r. Okay, so and now we keep going. So obviously there's going to be no phi component, but there will be a little bit of an r component, except that a little bit of an r component we're going to get rid of by way of the approximation that we have used to get rid of the other term in this also. Okay, so all we're going to end up with is the theta term. So let's do it. So the r component will have the form 1 over r squared sine theta, according to this, r squared sine theta, and then minus gr times the theta derivative of this, which is 2 sine theta 2 sine theta cosine theta. Okay, so yes, so what is this going to be? Well, the sine theta cancels. I'm going to be left with the cosine theta, and one of the r's cancels. So it seems that what I'm getting is minus 2g cosine theta, and that's going to be divided by r. Okay, so that's the r component. Okay, so that's the r component. So the r component, note, it goes something like e to the I k r over r squared. That's how it goes. Okay, and we already got rid in the previous analysis. Okay, so we already got rid of something that goes as 1 over r squared. Okay, so we are justified in throwing this r component away here too. Okay, and that's actually, there's further justification when we work out the theta term, believe me. So now we do that. So let's work out the theta term. So the theta component of the electric field is going to be, the theta component is going to be 1 over r sine theta, partial r, okay? And then here I'm going to have minus gr sine theta. Okay, so that's what I have. And so let's go in and so actually to start with, So I have to take this derivative first, but the sine theta cancels. So to start with, no, it does, sorry. No, I made a mistake, apologies. Here there's a sine squared theta, not a sine theta. Okay, so one of the sine thetas cancels. So sorry, let me start this analysis again. So my theta component is 1 over r sine theta, r derivative of minus gr sine squared theta. So let's get rid of one of the sine thetas and then do the derivative. So I'm going to have as my theta component, this here means theta component. I should really write e theta for this, because what I mean is the theta component. Not quite actually, because it's also multiplied by I over k. Okay. Um, I was just evaluating the curl first. Okay, so what do we have here? I can pull out the sine theta, so minus sine theta divided by r, and then I have to take some derivatives. Okay, so that's going to be, I pulled out the minus sign as well. So g prime, no, g prime r, that's going to be 1 plus g itself. Okay, and so what is this? So basically, so my g is this. Okay, so let's work knowing this. So my g of r is equal to k squared p e to the I k r divided by r. And my g prime of r is going to be k squared p I k e to the I k r divided by r. But the second term is going to be a 1 over r squared term. So there's a second term, but I can neglect that. So I'm going to keep this. So basically, that will just give me, that's going to give me, well, we can figure that out. But the other thing is that g divided by r also gives us a 1 over r squared term, which we can neglect. Okay, so we don't need this term either. We can neglect it. Okay, so what we're going to be left with when we put everything together is, so minus sine theta g prime r divided by r. So this r cancels, and g prime r is k squared p I k e to the I k r divided by r, but we also need to multiply by I divided by k. So what we're getting is sine theta, interestingly, so one of the k's goes away, sine theta k squared p e to the I k r divided by r. So that's what we get. And the interesting thing is that this is the same. So here we add minus k squared p to the I k r over r sine theta, k squared p sine theta e to the I k r divided by r. So we're actually getting the same thing as before. But actually, I think I made one mistake, and I know what mistake it was. That the theta term, there's one minus sign that I missed because of this taking this determinant. Okay, so I made a minus sign error, so this is actually minus. So, but the interesting thing is that E theta is the same as B phi in this case. E theta ends up being the same as B phi. Okay, so, and then the rest of the problem is actually to calculate things like the radiated power per unit solid angle, which is given by C divided by 4 pi and N dotted into E cross B. Okay, and maybe E cross B starts since we have complex here. So basically that gets rid of our exponential term. And what we're going to have here is, sorry, there's actually r squared here also. So what we're going to have here is, it seems, so when I do this E cross B, well, E cross B is easy here because we only have a theta an E theta, so an electric field in the theta direction, and the magnetic field in the phi direction. So we can ease, and actually they are the same. So in other words, this E cross B star is going to be sine squared theta k to the fourth p squared, and we determine that p divided by r squared. So basically our power radiated per unit solid angle is going to be c divided by 4p k to the 4 p squared, the r squared cancels, and then I have sine squared theta, okay? And in order to get the total power, that's going to be an integral, okay? So we have to integrate over the volume, over the, so that's actually, it's going to give us c k to the 4 p squared over 3, because obviously this, well, no, that's is that what it gives us? Let me just think. Yeah. So let me do this integral, but I seem to recall that that's what it gives us. But anyway, this is the radiated unit, the radiated power per unit solid angle, and then all you need to do is the integral. Sine theta d phi. Okay, so on the one hand, that gives us a 2 pi. So it's going to be c over 2. So the phi integral gives us a 2 pi k to the 4 p squared 0 p sine squared theta, sine theta d theta. And usually the way one can do this is to, instead of sine squared, let's write 1 minus cosine squared theta, okay? And then make the substitution x equals cosine theta, okay? And that indeed gives us a 2/3. So overall, for the total power, we're going to have c k to the 4th p squared over 3. Okay, and we determine p, so that actually is the full solution to this problem.